explore those. So I'm pasting these links for quantum simulator in the chat box. Now, going forward, yesterday we gave an overview of the QKD and quantum communications. So today I will explain how actually the keys are generated in quantum communication system. So first, let me share the screen. Yeah. So the screen is visible to everyone?
Yes, sir.
Yes, sir, it is visible.
Okay, okay. So yesterday I talked about QKD protocols, and there was one protocol called prepare and measure type of protocols. So in which there was an Alice and Bob. So Alice acts as the transmitter and Bob as the receiver. And so before going to that prepare and measure type of protocols, I will just in brief cover some of the basic quantum phenomena. I think most of you are aware of it. Just recap of the same. And all these prepare and measure QKD protocols are of type discrete variable, because here we are using discrete variables like time beams, phase, or polarizations. So we will come to know how how these protocols actually work and how the keys are generated. Then I will cover the quantum random number generators, how it is used, are the features, and then if time permits, I will cover QKD networks as I told yesterday. So these are some basic quantum phenomena. So you are all aware that in classical we have zeros and ones, but in quantum we can have that is represented in a slightly different way. It is called the Kate notation. So here you can see the notation differs from the classical point of view. So it is a Kate 0 and Kate 1, and this can be represented in a matrix form as well as a column matrix. But the new feature that quantum introduced is that in quantum the new feature that quantum introduced is the superposition. So in classical we have only zeros and ones, but in quantum any combination of zeros and one is also a valid state. So for example, there is a psi state and we can represent it as a alpha times kate 0 and beta times kate 1, and in the matrix form it can be represented as a column matrix of alpha beta. So these denotes a superposition state of zeros and ones. So what does actually superposition means? So actually there is a normalization condition. You can see that mod of alpha square plus mod of beta square equal to 1. So this is the superposition condition through which this superposition state is bounded. So this mod of alpha square and mod of beta square actually denotes, if I measure this superposition state, what will be the value, or what is the probability of getting a value of 0 or 1. So if the superposition state is such that if we measure it, it will be either 0 or either 1 with a certain probability of mod of alpha square and mod of beta square respectively. But until measure this state, it will be in a superposition state. So to explain this, there is a thought experiment proposed by Schrodinger. So he put a cat inside a closed box, and there is a poisonous element, and there is a hammer, and there is a radioactive element. So this is the hammer, this is the poison, and there is a radioactive element. So the setup is such that if in a given time, if the radioactive element decays, then the hammer will get activated and the poison will be leaked, and the cat will die. Now, if we don't observe this system, then we don't know whether the cat is dead or cat is alive. So this is called a superposition of life and death. So there is, if you see that there is 1 by root 2, because mod of alpha square or mod of beta square will be half. So this is the half 50-50 probability whether the cat is either dead or alive, until and unless you observe it. But if you make an observe, like if you open the door or if you see the cat, then you will get either the cat is alive if the radioactive element has not decayed, or the cat will be dead if the radioactive element has been decayed. So that this is the basic concept of superposition here given through a thought experiment like this. Now, the other principles that we use in QKD or quantum communications is called the no cloning theorem. So these theorems state that if we have an unknown quantum state, say for example, this is an unknown quantum state, we cannot make an exact copy of it. So in classical, if you have a data, you can make in multiple copies of it. For example, you have a data in your pen drive, you can make multiple copies. This is a digital data or classical data, but in case of quantum states, you can do that. So it is not allowed. Then the other basic concept is that is a concept of mutually unbiased basis. So what is the concept of basis? Suppose we make a state 0, and if we measure it in the same basis, then with 100% probability we can get 0. Now what is the concept of basis? To understand that, suppose we have I have a horizontally polarized light, and I use a polarizer that is either horizontally polarized or vertically polarizer, and I measure that state. So with 100% certainty, if I can state that this state is either horizontally or vertically polarized. But if I prepare a horizontal light using a rectilinear basis, but we measure it using a different basis, say for example diagonal basis, then we cannot guarantee with guarantee say that whether this state is was actually a state vertical state or it is an horizontal state, because we will get a 50-50 probability of getting a diagonal or anti-diagonal state. So this is the basic concept of BB84 protocol, is that if there is a mismatch in basis between the preparation and the measurement, then we cannot with certainty we cannot tell whether actually we have received the correct state or not. The other principle is Heisenberg uncertainty principle, that you are all aware that in certain conjugate variables, for example, position or momentum, photon number, and phase, we cannot measure accurately. We can measure accurately with some at the same time. We can measure actually. So there is a certain limit that this is governed by this inequality. Then the last concept is called weak coherent pulse. So as I told yesterday that at present we don't have very good single photon sources that can be used for QKD. So uh, we need to attenuate a laser to generate weak coherent pulse. So laser is a coherent source. We make it very highly attenuated to make a weak coherent pulse. So this weak coherent pulse, as I told yesterday again, it is based on photon or Poisson distributions, and the mean photon number we need to maintain less than 1 to avoid these multi-photon attacks. So that I already described yesterday. Now coming to the BB84 protocol. So as I told yesterday, it is the first QKD protocol. It was proposed by Bennett and Brassard in 1984. That's why the name BB84 from Bennett's B and Brassard's B and the year 1984. So it is again a prepare and measure type of protocol. And here you can see that this is the Alice structures. Here we have four lasers. So these lasers actually correspond to these four lasers contribute to preparation of state in four basis. So one is horizontal and vertical in rectilinear basis, diagonal and anti-diagonal in diagonal basis. And then this all these states are merged over a quantum channel. Then they are sent to the bob. Then at the bob there are four single photon detectors. Each detector is placed such a way that each detector clicks for this certain polarization, and this is called a polarization beam splitter. So this role of this beam splitter is to like if a light comes, so horizontally polarized light will go in this way and vertically polarized light will go in this way. And this halfway plate is for rotating the polarization, so that the this diagonally polarized light gets rotated. Then we can divide it in a two ways, like horizontal and vertical. So this is the basic concept of a BB84 protocol. We are using four polarization states. Now understand how the keys are generated. So we need to assign a bit 0 or bit 1 corresponding to either horizontal or vertical, and diagonal or anti-diagonal. So there are two bases and two bases and two bits like zeros and ones. Now we need to send these zeros and ones from Alice to Bob. So how do we send it? So suppose there is a random number generator. Typically it may be a quantum random number generator. So this random number generator is generating this bit pattern 0 1 1 0 1 0 1. So this is the random bit pattern. Now which also choosing a random basis. So this is rectilinear basis, rectilinear basis. This is diagonal basis. This is again rectilinear basis, like that. Now using this truth table, if we have 0 in a rectilinear basis, we make a vertically polarized light, so that it is shown here. Again, if we have 1 in rectilinear basis, it is a horizontal polarized light, it is shown here. Like this, we get this polarization state, and we transfer this polarization state through the optical fiber to Bob. Now this bob is again randomly choosing our measurement basis. So these basis choice and these basis choice are random. So because there is no relation between these two, because in some cases they match and in other cases they do not match. So this basis choice and this basis choice is completely random based on some random data source. Then in if the basis match, so if Alice measured prepared over a rectilinear basis and Bob also measured in a rectilinear basis, then we get the same state that was sent from here. But if there is a basis mismatch, we see that we can't get the same state. So only in the case where we get the same basis, like in these green columns, we get the same basis in which Alice prepared and Bob measured. We got the same basis. So that's why in this case we can get some key. Now, the thing is that how do Bob or Alice know that which basis has Bob chosen? So that is communicated over the public channel. So how it is communicated, that I will come to subsequent channels. The how this communication or the public discussions happens. So here the basic concept is that if there is a basis mismatch, like rectilinear with rectilinear and diagonal with diagonal, then only we will get the key bits. Or in other cases, these bits are discarded. The red columns are discarded. Okay. So if there is any confusion, please let me know, because this is the fundamental concept of BB84 QKD protocol. So if anyone has any doubt, please let me know at this stage. Please write in the chat box if there is any doubt. I think, okay, please explain again. Okay. So the basic concept is that I come back to this slide. This is the concept of mutually unbiased basis. So if we have a rectilinear basis and we prepare a quantum state using rectilinear basis, that will be either horizontal or vertical, and we measure it using the same basis, horizontal or using the rectilinear basis, then we can, with 100% fidelity, we can say that we can recover the generated state. So we have prepared a vertically polarized light using a rectilinear basis, and we have measured that vertically polarized light in the bob using that same rectilinear basis. Then we can get, with 100% confidence, we can say that this was said by Alice. Now if Alice prepares a vertically polarized light using a rectilinear basis, but the bob measures using a diagonal basis, then we cannot say that what is the actual state that was sent by Alice. So there is a 50-50 chance of getting either a diagonal or anti-diagonal basis. So if we get a decision, that will be wrong. So based on this protocol, actually the BB80 for QKD is designed. So here we are having a random bit pattern, 0 1s. This is a random bit pattern. Then we have a random basis choice. So this is random, this is again random, and this polarization is based out of this truth table, because this is our assignment. So in rectilinear basis, if the bit is 0, we generate a vertically polarized light, and if the bit is 1, we generate a horizontally polarized light. Similarly, in diagonal basis, if a bit is 0, we polarize a diagonal, and if the bit is 1, we generate an anti-diagonal. So we can map this 0 and plus. So 0 and plus is vertical, 1 and plus is horizontal, then 1 and diagonal is anti-diagonal. So you can see from this truth table, this is generated. Now in the bob end, bob will again choose this basis randomly. This basis choice and this basis choice are purely random based on some random data source. So if there is a match in basis, if there is match, then only we will get the correct result. So in this case, Alice sent 0 using rectilinear basis. So Bob measured it using rectilinear basis. So we recovered 0. Here we did not recover because Alice sent in rectilinear basis. So it was a horizontally polarized light, by while measured in the wrong basis, we got it as a diagonal polarized light. So this is wrong. So that's why we discarded it, because the basis did not match. So we cannot with certainty say that what was actually sent. So this is error. So we discarded it. So in those cases where there is a match, we get the shifted keys. So that's how the BB84 protocol is working. And there is a public discussion of basis, because Alice does not know what Bob will choose. So after getting those results, Bob will disclose his basis to Alice using the classical channel. Then only this shifted key will be used for further processing. So what are the further processing, that I will explain in the subsequent slides. Now, so what is the benefit of this protocol? Again, this protocol is information theoretic security, because this is we have rigorous security proof of this protocol. We can detect eavesdropping. This is well established and extremely studied, because it is the fast QKD protocol, and it is mostly used for free space QKD systems. But the challenge with this protocol is that we need to precisely control the photon polarization, because there are four polarization: horizontal, vertical, diagonal, and anti-diagonal, and we need to have correct control over the polarization, because in fiber the polarization may change. We need to track the polarization, and also for generation we need to have proper control over the polarization states. Otherwise, during generation only you can mismatch the states. And if there is a non-ideal source like that, we don't have a true single photon source, and if we use a weak current pulse, then some decoy states may be required. So that is another challenge. So decoy state means we are sending two pulses with varying intensity, so that the eve cannot decide between a decoy and the actual signal state. Now the second protocol that will come is called the distributed phase reference QKD protocols, that I told yesterday, that here we check the phase relation between two consecutive optical pulses. So there are two protocols. One is called coherent one way, and the other one is called differential phase shift. So first I'll cover the coherent one-way protocol. So this is the actual hardware setup of a coherent one-way protocol. So this protocol is based on, so BB84 was based on polarization, and this protocol is based on time bin. So how it is, how this protocol runs? So we have a continuous wave nano line with laser. Then this laser light is given to a intensity modulator, and then we have a quantum random number generator, and this is the source of this random data pattern zeros ones, and then this is given to an FPGA, and this FPGA then controls this intensity modulator. So how do we actually modulate the states? So there are two time slots. One is called early and the other one is called late. So if there is a photon in the late time slot, we call it a bit 0. If there is a photon in the early time slot, we call it a bit 1. And if there is a photon in both the time slots, let's call it a decoy state. So this is our actually convention. So you can use other conventions also. That does not change the protocol anyway, but it is only the convention. How do you define bit 0 and bit 1? Now what happens? This time slot, the yellow part or the green part is typically 125 picosecond, and the repetition rate is around 500 megahertz. So this period is one nanosecond each period. So total 2 nanosecond, then it is becomes 500 megahertz. So this, if there is a, as I told, if there is photon in late, it is bit 0. If there is photon in early, it is bit 1. So this we have a laser, we modulate it, then we highly attenuated this laser pulses such that the mean photon number, that is mean photon number per pulse is less than 1. Then we send it over the quantum channel, that is an optical fiber, to a bulb. Okay, so this is how the Alice works. So Alice, we have the lasers, we have the lithium niobate based intensity modulators, and we have an attenuators. This is typically controlled by a variable optical attenuator. Then we send it to Bob through the optical fiber. Then in the Bob we have a splitter. So this is an optical passive splitter, power splitter. So it is a 90:10 ratio is typically chosen. So 90% of the photon will go to one single photon detectors. The other 10% goes through a delay line interferometer. Then this delay line interferometer is connected to a single photon detector. So how the keys are generated? So the 90% photons that will go to this detector, that will contribute to generation of the secure keys, and that other photons that will come here, that will that in that we have a delay line interferometer. So this in the interferometer we will check the phase relation between two consecutive pulses, that will give some clicks in this detector. So this will enable us to check the eavesdropping in the channel, because if someone tries to eavesdrop on your channel, then the phase relation between these two consecutive optical pulses will be disturbed. So the clicks in these detectors will vary, and this is reflected in terms of a parameter called visibility. So if there is a disturbance in your channel, or there is an eavesdropping in the channel, this phase relation between consecutive pulses will get disturbed, and that will reduce the visibility. So this aspect 2 will contribute to check the visibility, that is an indicator of the eavesdropping on the channel. So typical visibility is more than 90%, but if the visibility drops, we need to check whether there is any eavesdropping or not. And the other aspect contributes to the detection of the bits, that will contribute for secure key. So bit 0 and bit 1 will detect here. So by chance, if decoy state comes here, we will discard that. And similarly, if the bit 0 and bit 1 comes here, we will discard that. So this aspect is only responsible for detecting bit 0 and bit 1, and this aspect is only responsible for detecting the decoy state. So if because it is a splat passive splitter, so it may so happen that sometimes bit 0 or bit 1 will come here, sometimes decoy state will come here. So we need to discard that. So that's how the protocol is designed. So this is the coherent one way. Here the basic concept is the encoding is done in the time bin, and in BB84 the encoding was done in polarization. Now the third protocol that we have is called the differential phase shift protocol. So the protocol architecture is similar to coherent one way, but it is slightly different in the sense that here instead of time bin or polarization, we use phase. So what happens in this case? We have a continuous wave narrow linewidth laser as usual. Then we have the intensity modulator also. But through the intensity modulator, we are only making the pulses. Then these pulses are phase modulated using again lithium niobate based phase modulator. So we are having these pulses, and if there is a QRNG, so if the QRNG data is 0, we do not do any phase modulation. But if the QRNG data is 1, we add a pi phase using this phase modulator. So this is discrete variable. So only there are two phases, 0 and pi. If QRNG data is 0, there is no phase change, that is the relative phase is 0. And if the data QRNG data is 1, So pi phase is added. So that's how the system works. Now after this phase modulation is done, again these are attenuated heavily, and it is made sure that the mean photon number is less than 1. So typically the mean photon number for coherent one way is zero point 0.5, and for differential phase shift it is kept at zero point 0.2. This comes from actually the theoretical security proof. Then these pulses are transferred to again bob. Here also the bob contains two single photon detectors. We have a 1-bit delay line interferometer. So this is actually the 1-bit delay line interferometer. So what will happen in this bob? So this pulse will interfere with this pulse. So how? So just follow the animations. So this is 1-bit shifted. So I we have sent at 00 pi 0. So it is 1-bit shifted. Now so this will now interfere. So if 00 interferes, then this is a constructive interference. So one SPAD will click. If 0 and pi interferes, this is a destructive interference. So another SPAD will click. So based on this, whether which SPAD clicks, we will get to know whether 0 was sent or 1 was sent. So this one SPAD is dedicated for detecting the zeros, and other detector is dedicated for detecting the ones. So depending on which detector clicks, we get to know whether 0 was sent or 1 was sent. So if we send, if we send, there is a 00 interference, that means a constructive interference. There was no phase difference. So this detector, the detector in the constructive of this delay line interferometer will click. If there is a pi phase difference, the detector in the destructive arm will click. So based on which detector clicks, we will get to know whether 0 was sent or 1 was sent. So here the degree of freedom that we use is phase, but in case of current 1 it was time mean, and for BB84 it was polarization. Now the questions comes, we have sent some quantum states and we have detected in Bob. Now how actually the keys are generated, because till date we have only detected the states, but we did not get the actual key. We did not get a feel of how the actual key is generated. So these coherent one way and differential phase shift, their protocol are designed in such a way they are inherently secure from an attack called photon number splitting attack, because here we keep the mu less than 1. So if as I told yesterday, we cannot keep mu more than or equal to 1, because that will result in multi-photon pulses. So in these states, in this DPS, there is only one parameter, that is the quantum bit error rate. But for coherent one, we also check the visibility. So here, if there is any eavesdropping, then again the phase relation will change between these two pulses, and the QBR will go up. So using the QBR measurement only, here we will get to know if there is any eavesdropping or not. So here both the detectors are contributing to generation of secure keys, and in case of coherent one way, only one detector is contributing to generation of keys. So typically you will see that in coherent one way the key rate is half of what we get in DPS. So in typically it is around 1 kbps for coherent one way, say up to 23 dB of loss, and for DPS QKD it will be around 2 kbps for the same loss. So is there any doubt in coherent one way or DPS architecture? Okay. So these are the steps that we follow to generate the actual secure keys. So how the actual secure keys are generated? So these are the steps. So we have a classical channel authentication, qubit transmission, then synchronization, then rock shifting, then error correction and privacy amplification. So these are the steps involved, but how these steps are operated, that I will show you in the subsequent slide how these are actually happened. So I will take a small example of Alice and Bob. So Alice and Bob, they are connected using a quantum channel and unidirectional quantum channel. That quantum channel is from Alice to Bob, and the classical channel is from by classical channel is bidirectional. So please follow this animation so that you can understand how the key is actually generated in a prepare and measure QKD protocols. So for example, first Alice and Bob, they are powered on. So they will check each other whether it is the intended Bob or it is the intended Alice. The process is called classical channel authentication. So there is a preset key inside Alice and Bob. So they matches those keys using classical channel to check whether it is the intended Alice or Bob. So this process is called classical channel authentication, and this is based on an algorithm called Poly 1305 MAC based authentication, message authentication code MAC based authentication. Using those algorithms, Alice and Bob are authenticated first. So the purpose of authentication is that there should not be in a man in the middle type of attack, such that some third party is pretending to be Bob, or some third party is pretending to be Alice so that he can generate some secret keys using that. So to prevent that, Alice and Bob must be authenticated when they are first powered on. So if the authentication is suppose successful, then we'll proceed to the next stage. So in the for example, I have taken a 30 bit long pattern, but in typical it is a continuous process. It is running at around say 500 megahertz or 1 gigahertz speed. So for example, I have taken a 30 bits of raw data that is being transferred from Alice to Bob. So for BB84, these 30 bits will be encoded in phase polarization, and for differential phase shift it will be encoded in phase, and for coherent one it will be encoded in time bins. So that will not change anything in the key generation process. Only thing is that the what are the degree of freedom that you are using. So here we have taken 30 bits. Then these 30 bits are transferred over the quantum channel to Bob. Now what will happen? Every channel will have some loss because the optical fiber typically have 0.2 dB per kilometer loss for lab grade fibers. So during that quantum channel transmission, some of the photon will get lost in the channel, because here we are sending at max one photon per pulse. So there is no attenuation, because if either the photon will get transferred or it will get absorbed. So the attenuation will not result in terms of reduced power, but it will result in the number of photons missing per pulse. So because one photon is there at max per pulse, so either the photon will reach or it will not reach. So we have sent 30 bits, and for example we have received 12 bits. Now you can see that the dashed area we have missed the photon that have not been reached, and the red photons, red ones or zeros, that is the bits that we have received in error. Now the error can come due to channel noise or due to the detector imperfections or anything. So there will be always be some error in the channel transmission process. So we have sent 30 bits and we have received 12 bits. So this is the qubit transmission phase. Now the role of quantum channel gets over. So quantum channel is unidirectional. It is only sending the qubits from Alice to Bob encoded in either polarization, time bin, or phase. Now if the quantum channel role gets over, now the classical channel comes into play again. Earlier it was only for earlier we did the classical channel authentication. Now again it will come into picture. So the Bob will disclose at what time. Say for example, we have not received anything in T1. We have received something in T2. Again in T3 it is missing. Again T4 we have received something. So Bob will disclose these time values T2, T4, T6 like that to Alice through the classical channel. Now Alice and Bob are earlier synchronized, so they know, Alice knows in which time it has sent something. So it will discard the remaining bit pattern in which Bob has not got anything. So it will keep only those values for which Bob has received something, those corresponding to these time slots. Now both of them are left with 12 bits. But you can see that these 12 bits is not identical with these 12 bits, because there are two errors in it. And this error happened during the transmission or during the detection. So these are not identical. So this step is called shifting. So shifting is basically a filtering step. We sent 30 bits. Due to channel loss, only 12 were received. Some were received in error. So then Bob transferred the timestamps corresponding to the received bits to Alice using the classical channel. Then Alice discarded the remaining 18 bits because they are not received by Bob and they are lost in the channel. So now both of them are left with 12 bits, but they are not identical. Now Bob will again disclose a subset of it. So earlier it was left with 12 bit. So it will take a subset, for example, 1 bit, and it will disclose the time slot and value. And it will send to Alice again through the classical channel. Then Alice will calculate the percentage of error in the disclosed bits. So typically this disclosed rate is typically kept at 3%. So suppose you have received 1000 bits, so 30 bits will be disclosed at random, and these bits are chosen at random so that to check the quantum bit error rate. So suppose there are two errors, so 2 by 30 will be your quantum bit error rates in that case. So here, for example, we have taken only one bit just to demonstrate how the key generation happens. So we have disclosed the bit time slot along with the value. Then Alice will calculate the QBR. Now each protocol has a QBR threshold. This threshold is decided from the theoretical security proof. And for BB84, this threshold will be 11%. And for coherent 1A and differential phase shift, this threshold is typically 5%. So if the quantum bit error rate in the disclosed bits are less than the threshold, then we proceed to the next step. But if it is more than the threshold, the channel is not secure, and we discard whatever was sent and we start afresh. So that's how the system works. Now in this example, only one bit is disclosed, so they will leave with 11 bits. So only one was disclosed. They are 11, left with 11 bits. But again, you can see that these 11s are not identical because some of the undisclosed bits also have some errors. Okay, so these are not identical. You can see that here these red ones are not matching with the Alice because during transmission or during detection they face some errors, and the bit got flipped. So these are the left 11-bit pattern that are left with Alice and Bob. Now they know that they know there may be some error, there may not be some error. So to check that, they run some error correction algorithm and they does the parity exchange. So typically the error correction algorithm that is used is called low density parity check or LDPC. So after that LDPC process, their errors are corrected. Now both of them are left with the same identical pattern. So you can see that Alice is having 11-bit pattern, Bob is also having 11-bit pattern, and they are after the error correction they are identical. So this is the error correction step. But during the error correction step, we are doing the parity exchange in the classical channel. Now the classical channel is having the classical communication, so there is no quantum security in this classical channel. So during this parity exchange, any eavesdropping can listen to the message that are being exchanged over the classical channel, and he can get an idea of the secure key that is being generated. It is not the 100% of idea, but he can assume some, he can get some information of the secret key that are being generated. So to prevent that, we use an hash based algorithm to actually compress these 11 bits to a smaller number by, say, for example, we have compressed almost 90% from 11 bits to using an algorithm, hash based algorithm, we get 2 bits. So these 2 bits are again identical because we are using the same hashing algorithm at both the ends. So we are left with a small number of bits at both Alice and Bob. So this step is called privacy amplification, and after the privacy amplification stage, this is your actually secret key. So that's how the secret key is generated at both ends of Alice and Bob. And you can see that we started with 30 bits that we transferred to quantum channel. Then 12 bits were received. Then we do the shifting process. We disclose the timestamp. Then Alice discarded the remaining 18, but they are not identical. Then we do the disclose to check the quantum bit error rate randomly by selecting some bits. That is typically 3%, as I told. So after the disclosed bleeds or at the QBR threshold was QBR was less than the threshold, then we proceeded to error correction. And as the value was disclosed at this state, we discarded those values, right? So we are left with 11 bits. And then after we corrected those 11 bits, they become identical. But during parity exchange, some information got leaked out. So to prevent information leakage, we compress this. So what is the benefit of compressing is that suppose 2 bits of that are being sent from Alice to Bob. And if you repeat this process, you will keep on storing the keys in your memory. As yesterday someone was asking that how many qubits are required, so I think you have now got a feel like how the qubits are transferred over quantum channel. Then the classical channel comes into picture for the post processing steps. So you can see that all the post processing like shifting, error correction, and privacy amplification all are taking place in the classical channel. The role of quantum channel ends once we complete the transfer of qubits.
Hello, sir.
Yes.
May I audible?
Yes, yes, ma'am.
Sir, here in this case, we are having 30 bits, and from that we have generated 2 bits secret key, right?
Yes, ma'am.
Now we require for AES encryption 256 bits, right?
Yes, ma'am.
So as we are generating continuously, so from that pool we will be collecting 256 bits, and that will be shared as a key.
Yes,
Am I
ma'am.
right?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so it is continuously generated, and how many number of bits will be I
Ma'am,
mean, just like
actually, what we do is that we are continuously generating and we dedicate a memory inside our Alice and Bob that this is the
okay.
memory size that will generate the keys. Now, if your memory gets full and you are not getting any key request, then the keys will get replaced. So that's how the
Okay.
system occurs. So suppose you have an 1 MB of memory, so 1 MB keys will be stored at all time. Yeah, and
Fine.
if there is a request, then 256 bits will be supplied.
Okay, okay. One thing.
Yes.
Second thing, all these process that is shifting, error correction, privacy amplification,
Hmm.
all are taking place on classical channel, right?
Yes, yes,
And
ma'am.
quantum channel is our optical fiber channel, right?
Ma'am,
Now,
classical channel is also optical fiber based.
Okay, so both are basically optical fiber.
Yes. Both
Okay,
are
so
optical
one
fiber.
is just yesterday one was said that it is a dark fiber.
Yes.
What is the meaning of that dark fiber
Yes, ma'am.
then?
Actually, I am coming is that what is that quantum channel and classical channel both are optical fiber that is already we are using in the telecom networks. There is no separate kind of fiber.
Separate.
It is the
Okay.
same fiber. But the thing
Okay.
is that in quantum channel we are sending single photon pulses, right? So
Right.
if you measure the optical power level in those of quantum channel, it will come around minus 75, minus 80 dBm. Okay.
Okay.
But in classical communication, we use the power in a much higher magnitude. Say it will be around 0 dBm or minus 3 dBm. Now,
Correct.
the thing is that due to this power mismatch, if the quantum channel and classical channel are transmitted over a same fiber using WDM, then
Hmm.
there will be coupling from classical channel to quantum channel. So this
Hmm.
coupling will act as a noise to the quantum channel and it will degrade the performance. So that's why it is recommended that you transfer the quantum channel over a dark fiber in which there is no other signals.
Okay, okay. So that will be separate fiber. For example,
Yes,
in our telecommunication, we are using optical cables, and in
yes.
cable there are multiple
Multiple cores.
fibers
Yes. So you
running.
need one core actually in that.
But
Yes.
the one core we will take as a dark fiber, where we will be having which will work as a quantum channel,
Right.
and
Right.
on other fiber we will be having all these operations, right,
Yes,
sir?
ma'am. Yes, ma'am. Yes.
Okay,
Right.
okay.
Yes.
And now whenever key is required, so same key will be used for on the third fiber for in general communication, right?
Yes. Yes. Third fiber will be used for your actual encrypted traffic.
Communication, yes,
Yes, ma'am.
encrypted
Yes.
one. Correct,
Yes.
correct.
Yes.
Okay,
Yes.
sir, that's all. And
Yes.
one more thing, sir, here, if I say there is a word called key rate,
Yes,
one
ma'am.
word which is used here is called key rate. What does it
Yes.
mean? Key rate means
Ma'am,
number of
key rate
keys
is that
generated per
here is that
second.
yes, ma'am. The key rate concept is that we are sending this beat pattern. Here I have taken a static example of 30 bits, but in
Okay,
general it is we are transferring at a rate of say 500 megahertz. Okay. Now
okay,
due to all this process and compression, so you can see that from 30 I have come to 2. So
correct.
and there is a channel loss there. So actually the key rate is that in which rate you are generating the secure keys at your memory. So typically the rate that we get is around 2 kbps for differential phase shift and 1 kbps for quadrant one way. So when we are doing a 90% privacy amplification, so 90% privacy amplification means we are compressing it by 90%.
Okay, okay.
So
So,
yes.
हाँ, yes, sir, बोलिए. Yeah,
So typically the thing is that in DPS we are getting around 2 kbps. For quarant one it is around 1 kbps. So that's how the key rate. Now 1 kbps means 1 kb kilobits key per second. Okay. Now
okay,
we are getting a request of only 256 bits, and the
correct.
keys are not changed every second. So we can configure at how many interval you can change the key. So suppose your keys are changed every 2 minutes. So there is a huge margin between the generation and the consumption rate.
Correct, correct. Correct. Okay. One more thing, sir, just we have converted 30 bits into 12 bits. Convertedly, we are getting, right?
Yes,
It
yes.
is because of basis mismatch as well as a
Yes, ma'am.
channel
Yes,
noise,
ma'am.
right?
Yes, ma'am.
So,
Yes, ma'am.
both the things will be covered here, right?
Yes,
One
yes.
more
Both the
thing,
things are
if
covered.
I increase the fiber length, see, our telecommunication fibers are having length 60 kilometers, 80 kilometers,
Yes,
like that.
yes, yes,
Now, as we know that as the signal propagates through optical fiber, there is attenuation as well as
yes,
dispersion. So
yes.
attenuation will not play any role. Attenuation will not play any role because we are transmitting the matlab information over quantum channel at very low power level. So amplitude will reduce, right, sir? So how I
No,
will be
no,
able to
no.
detect at Bob side?
No, no, ma'am. The thing is that when we are doing classical communications, so suppose you are transmitting 0 dBm of power, right? Now,
Yes,
0 dBm of power and there is a channel loss of 30 dB, for example.
correct,
So
correct.
in the receiving end, you will receive minus 30 dBm of power, right?
Yes,
But in this case, the issue is that we are transferring a single photon level of signals. So each pulse is having at max one photons, right? Now, in
yes.
this case, the attenuation will happen because the fiber attenuation is there. But here, the effect will be seen in such a way that you are sending 1,000 pulse, for example, and due to attenuation, maybe there are only 200 pulse will reach there actually. The remaining 800 photons will be absorbed in the channel.
Okay, so remaining 200 pulses, we will be getting the information at the Bob
Yes,
side.
because here
Then
you
Bob
can,
will
yes,
choose a
because
particular random basis and then detect what is transmitted, right?
because, ma'am,
So,
actually the thing is that here we took 30 bits and we got 12 bits because of the channel attenuation. Okay. Then,
okay.
because there is no basis mismatch here because only the 12 reached there. Only the
Sorry,
12.
I didn't get why basis mismatch is not there. I didn't get it. Basis,
Ma'am,
so basis mismatch will be there, right? Bob will be selecting random
no,
basis.
no,
So
no, ma'am, let me explain. Actually, the thing is that we have taken 30 bits, and due to channel attenuation, 12, only 12 bits reached there, and there are some bits that were received in error due to channel noise. Okay. Now,
okay,
if you are telling that due to basis mismatch, what will happen during this discussion, they will come to
correct.
know that they are here. Actually, here this example is for coherent one and differential phase shift actually,
Okay, okay.
but for BB84 along with these time slots, Bob will also disclose its basis for BB84.
Okay, okay. So
Okay.
here there is no basis, disclose only the bits from
So
time step
actually in
and
coherent
the.
one there is no basis because there is only one basis time or phase. Okay. But
Okay, okay,
in
okay.
BB84 there are two bases rectilinear and diagonal. So
Diagonal,
in
right.
this stage in this stage for BB84 Bob will also disclose the basis as well as time. So if there
Correct.
is time if Bob has got a click in say for example T2, but if there is a basis mismatch then T2 will also get discarded in case of BB84.
Okay, okay, okay.
But
Got
in
the
current
point.
on there is only one basis, so the basis mismatch will not happen here because we are only using
Correct.
either time or phase. So this
Okay, so
basis
here
mismatch
only
will
the
take place in
attenuation
this
losses
stage.
will be there. Here
Yes,
only attenuation will be there.
yes,
Okay,
yes, ma'am.
okay. And what, sir, what about one more? Since you are saying that we are transmitting 800 pulses and out of that we are getting only 200 pulses at the
Huh,
bob side. Now,
huh.
since the length is very large, so there may be dispersion also, sir.
Ma'am, actually, the thing is that the distance of QKD that you see if is typically limited to around say 150 kilometer to 200 kilometer. Okay. So
Okay,
and we are using a very narrow pulse width of 125 picosecond with very high quality laser. So laser line width is also very less. So the dispersion
okay.
effect will not be very prominent here.
Not well. Okay, okay, okay. And also we are using 1.5 micrometer. So attenuation will be less and
Yes,
dispersion
yes,
we are okay, very
yes,
narrow pulses.
yes,
So both
yes,
the phenomena can be
yes,
compensated here.
yes, yes,
Okay,
yes,
sir.
yes, yes,
Okay, thank you so much, sir.
okay.
One more thing, sir.
Yes,
For
ma'am.
QPD, which book we can use, sir?
Ma'am, I'll send
Is
you in
there
the
any
chat.
book?
I'll send you. I'll send you, ma'am.
Okay, sir. Thank you.
Okay,
Thank you.
okay,
Yes.
okay.
And one, sorry. Yeah,
Uh,
one more thing, sir. Suppose
mhm,
I have to demonstrate it as an experiment in our lab. I'm teaching this subject like quantum communication starting. Matlab, it's just a start. But in
uh-huh,
the third semester, it will come as a quantum QKD,
uh,
quantum communication part. So if I have to perform experiment related to the this, what we can do? Because already we have shown simulator to the student. Students have prepared complete the IBM Qiskit code and they are able to demonstrate that this is the key
mhm.
generated. But suppose we want to perform on the hardware show in the lab, is it
Yeah,
possible
ma'am,
to
actually
show?
the thing is that in the subsequent slide, I will show that we have supplied our QKT system to multiple educational institutes. So
Okay,
we have actually this coherent one-way and differential phase shift QKT systems are a bit costly. So we have customized this solution for educational institute. Mostly they have some lower budgets. So I think there are four institutes who have already procured. They are offering some courses and they have written
okay.
some paper as well. So I will show in the subsequent slides.
Sure, sir. Thank you.
Okay,
Thank
okay,
you
ma'am.
so much.
Okay, ma'am.
Sir, but only thing book is required.
Okay,
Please
ma'am.
share the details
I'll send,
for.
ma'am. Yeah, I'll
Yes,
send.
sir, so that we
Okay.
will get.
Yeah,
Okay,
okay.
thank you
Okay.
so much,
Okay.
sir. Thank
Okay,
you.
ma'am.
Hello, sir.
Yes, ma'am.
Hello, good evening, sir. Sir, I want to ask one question. For example, like if we have hybrid modulation techniques, right? So if we use DQPSK along with PCM as a hybrid modulation technique, right?
Mm-hmm.
So I'm having confusion is that you are saying that we can use a traditional optical fiber as a quantum channel. Then, sir, how I can differentiate between classical channel and quantum channel if I'm using same fiber in both the channels?
Ma'am, it is not the same fiber. I am taking the telling that it is the same type of fiber.
Okay, okay.
I am not telling the same fiber. I am telling that it is the same single mode telecom fiber. Same
Okay.
type, not the same fiber.
Okay, okay, sir.
So that's why I'm telling it is a dark fiber for quantum channel is recommended. So dark fiber means a separate core for quantum channel and another core for classical channel.
Okay, sir.
Yeah, so it is a single mode fiber that is already deployed. I do not need any special type of fiber.
Okay, okay, sir.
Yes.
Am I
Now,
audible?
yesterday someone asked about multiplex QKD systems. So this is an example of
Hello?
multiplexing. So how actually multiplexing is happening is that you know that quantum channel is from Alice to Bob. So it is unidirectional. Classical channel is bidirectional. So we have two fibers, one from Alice to Bob directions, one and the second fiber is from Bob to Alice directions. So here we can see that we have a QKD Alice here. The quantum channel, the classical channel transmit, and there is a data link for 100 Gbps rate. So these three channels of different wavelengths are multiplexed on a single fiber. So we have the 100G transmit, quantum channel, and the classical channel transmit from Alice to Bob detection in one fiber using WDM. They are in the 100 gigahertz separation as the DWDM link. Then they are again demultiplexed at this place. Then 100G goes in this equipment, and the class quantum channel and classical channel comes into QKD systems. And for the reverse detection, there are only two lambdas, 100G and classical channel. So you can see the red lines, 100G and classical channel from Bob to Alice detections. So that's how this multiplexed QKD system is operating. So you can see our experimental results in this paper. I can send the paper if required. So this is actually the wavelength division multiplexing, and we are operating at 100 gigahertz spacing. But the only thing is that due to nonlinear effects, it is recommended to spare the adjacent band of that adjacent line of that quantum channel. So if you are using quantum channel at say channel 34, so it is recommended that you leave channel 33 and 35. So it will be there will be some immunity from noise. And in the receiving end, you in the quantum channel you put a narrow band filter to filter any Raman scattering or any noise. So that's how this multiplex system operates. So here you are using the same fiber that is already carrying some data. But you can see that here I have mentioned 50 kilometer of fiber spool because the distance is limited due to the noise coupling for high power signals. So that's why it is not suitable for long distance. Basically consists of both Alice and Bob in a single box. So this is for increasing the distance. So this is this Alice of this box relay node, and Bob will comprise of one link, and Bob and Alice will comprise of another link. So this will actually to make the distance here twice. So with these three nodes, so this will be 100 kilometers, for example. This will be another 100 kilometer or 150 kilometer, for example. So that's how this relay node we have designed as a. So it is the purpose of designing a relay node is that we can have Alice and Bob in cascade, but having a relay node will reduce the size, weight, and power consumption. So that's the benefit of having an integrated relay node. For a protocol called cow slim. Now, what is cow slim? So I'll just go back in the previous slides. So this is the actual setup of cow. So you can see that this cow box consists of two detectors. So, but in cow slim, we remove this detector and this delay line interferometer, so the cost come down. So some of the feature will not be there available for cow, but it will be a good setup for having to demonstrate the actual key generation process to the student. So we'll have a GUI that is connected using our system, and we can open it on laptop or desktop, and you can have a feel actually the how the keys are generated, what are the intermediate steps that is shown in this diagram, like all these steps like shifting, error correction, private amplification. You can change different parameters and see what is the effect. You can put in a fiber spool or attenuator in between your channel and vary those parameters, and you will get a plethora of experiments. So that will help you to actually demonstrate the students actual fiber based QKD systems. So we have given those systems to multiple educational institutes. So one of them, the first one that they took is called GIIT Noida, Jaipur Institute of Information Technology. So they took it long back in February 2022, and they are still using it. They have published some papers using this system also. Later on, we gave it to an university called DY Patel University in Mumbai in 2024, and then we have given it to Arnet India, Arnet in Chennai. Then we have installed it in NSUT Delhi, and then we have recently got an order from Mahindra University Hyderabad. So so there are private universities as well as government universities, both are using our systems, and we have done multiple field trials as well in Indian Army, Indian Air Force, and one link is operational with the live traffic that is between the Sanchar Bhavan, that is Department of Telecom, and NIC headquarters in Delhi. So entire traffic between these two offices is encrypted using the keys that are generated by C.QKD system. And we have some TOT partners. So TOT partners are actually the bulk manufacturers. So they have bid for some tenders, and now they have supplied two links to scientific analysis group in DRDO, and they have recently secured another tender from DRDO. So you can see that these are the competitive tenders. So other private bidders have also bid for that. So you can see that our systems are really cost effective. And for educational institutes, we have customized the solution to quote in a low price so that it can fit in their budget. And we have a list of experiments that you can perform with those system. And recently, AICT has come up with a syllabus for UG minor, and this last year, I think in December, they have launched that. And this system can actually support to help demonstrate those UG minor curriculum in the using this our QKD system. So these are some of the appreciation letters that we have received from the educational institutes, from JP Institute, then DY Patil University and ARNET. So you can see that all of them are using it. JP has published some good papers using our system. So and you can see that paper reference is also given here. These are some of the patents that we have got. One patent has been already filed. Three patents we have got in from Indian Patent Office, one from US patent as well. Then we have published some research papers, and this paper is for that multiplex system that I showed you. So you can have a look in this paper later on if you are interested. And we have our QKD systems have also secured multiple awards from Aegis Gahambrand Award, Technology Software Awards like that. So this is our technology partners. So they are actually the bulk manufacturers for our systems. We have four manufacturers in India: ECIL, New Age, Skytel, and Chip Spirit. These two are startup. This is a PSU, and this is a private company. Now I will come to quantum random number generator. So quantum random. So what is a random number generator? So basically, in different applications, we need to generate truly random numbers like zeros and ones of sequence. So it has many applications in secure communications, cryptography, or in casinos. They have very good applications. And for quantum random number generator, the basic phenomena that we use is called uncertainty principle or superposition or entanglement. Obviously, these are the basic quantum phenomena. So while coming to QRNG, there are other two types of random number generators. So you must all be knowing that there is something called pseudo random number generator and true random number generator, and the third one is QRNG or quantum random number generator. So what are the difference? So PRNG is basically use a mathematical formula, and based on that formula, the next states are determined. In case of TRNG, this is called true random number generator. So it is using some classical phenomena, for example, clock jitter. And QRNG uses some quantum physics phenomena. So what are the phenomena we'll see in the subsequent slides. But the issue with PRNG is that it requires a seed. And if we know the seed, then the next sequence are highly predictable. So that because it is governed by a mathematical function. So that's why it is earlier it was used heavily, but it is weak for cryptography. But it is mostly used for simulation and some non-critical applications. But TRNG is secure, but it is think that in some certain condition it could be predictable again. It is also used in cryptographies and lotteries kind of thing. The most recent one is called the QRNG, and it is the most secure form of randomness source. So it is fundamentally unpredictable because it is using the laws of nature or quantum physics. So it is mostly used in QKD and other high security applications. So our QKD systems, Alice and Bob, had a QRNG chip inside. So the randomness source that I have showed in the 30 bits of example. So this random pattern is being actually generated by a QRNG. So what should be the properties of a QRNG? The first property is that it should be uniform. So uniform means over a long sequence, the zeros and ones should appear at random, and they should have almost 50% probability of having a zeros and over a long sequence. The second property is that it should be scalable. Scalable means if I extract a subsequent from a long sequence, that should also be random. Then it should be consistent, like different. It should not behave different in different times differently. So it should have a consistency in its operation. Then the other property is it should have forward secrecy. So forward secrecy means if we know the present bit sequence, we should not be able to predict the future sequence. So that's all called forward secrecy. And the other one is called the backward secrecy, means if we know the present sequence, then we should not predict know about the previous sequence. So that's why it's called backward secrecy. And again, it should be stable over time. This is more like a consistency because the temperature may vary, the environmental conditions may vary, but it should operate stably, and its other parameters like forward secrecy, backward secrecy, or its randomness should not depend on some other parameters. So that's how these are the different properties of QRNG. Now there is some myth versus reality that it is sometimes called that these QRNGs are always perfectly random. But the thing is that in nature, the quantum randomness is perfect, but we are using some ADC, DAC kind of thing to actually sample that random phenomena and get the outcome. So in our actual process, there may be some errors. So this QRNG may not be always very perfect. Then QRNG are immune to hacking or tampering. So it is again the physical process you cannot hack or tamper, but we are after getting those physical phenomena, we are actually processing those data. So in this process may have some backdoors, so that can be that can make the system vulnerable. All QRNGs are equally secure? No, because quantum phenomena are secure. But again, it depends on how we actually implement it in a hardware. How what are the ADC and DSC that you are using? They have some finite quantization levels. So the security will depend on those parameters. And the QRNG behaves best with respect to randomness testing. So there are some tests for randomness, but some QRNG may pass all randomness testing, but some may not pass. So that is another debate. So how to test a QRNG? And sometimes it may happen that if your design is not proper, so some classical RNG like TRNG may also surpass the randomness value with respect to QRNG. So everything depends on how you design and how you manipulate the quantum phenomena. So, based on how you design a quantum QRNG, there are two types of things. One is called optical quantum phenomena. So here is thing is that we have a single photon source, and there is a beam splitter. So the beam splitter property is that it will either reflect a single photon or it will transmit a single photon. So if we send a single photon to a beam splitter, there is a 50-50 probability that either it will be reflected and it will be detected in this single photon detector, or it will be transmitted or detected in this single photon detector. So suppose if it is reflected, we assign a bit 0, and if it is transmitted, we assign a bit 1, then there is a 50-50 probability of getting zeros and 1. So typically this is actually a quantum random number generator. So if you keep on sending single photons to this beam splitter, and then we record the detection in these detectors, we should get a random sequence. Then other option is having an amplified spontaneous emission. So the lasers are having some amplified spontaneous emission. Not this is basically an actually noise. And if we implement some interferometric kind of thing and we place a photodetector here, so we'll see some fluctuations in the detection current. So using that fluctuation that is also a random phenomena, so we can use it as a QRNG, because we can then sample these photodetector detections current values using an analog to digital converter, and then we can get some random values. So these are based on optical phenomena. Other phenomena is the non-optical quantum phenomena can be radioactive decay. So that radioactive decay is also a random phenomena by nature, and we can then digitize those electrical signals based on some random radioactive decay. And the other phenomenon is called short noise. So short noise is basically in any circuit there may be short noise. So it is again random phenomena. Thus we can again detect those short noise and convert it to bit patterns. So these are some of the phenomena. Now I have taken this diagram from the ITUT standard. So this denotes what should be inside your QRNG's source. So first we have that quantum state preparation. So the quantums for this example, so the quantum state preparation is the single photon generation. Then we'll be measure the state. So measurement is basically detecting the using one of the SPDs. Then we'll get the raw data. Then we need to make some post processing and we need to verify the entropy. So entropy is measurement of the randomness. So how random is your data is the measurement of your entropy. Then there is some source parameter monitoring, is that whether your single photon source is operating properly or not. So this type of monitoring and feedback actually is there inside a QRNG. So this is I taken from ITUT. It is also there in the TEC-GR for this. Now, how do we actually measure the randomness of a QRNG or any RNG per se? So there are two very popular tests. One is called the NIST statistical test suite. So this is a free software that you can download, and you can evaluate you can take any random sequence and then you can run this software, and this will perform different tests and it will come up with a report whether this sequence is actually secure, random or not. Then another test is called Die-Hard test. So it was developed by George Marsagila in 1995. So it is also consists of some tests, but it is the NIST test that is most widely used nowadays for validating the QRNG. And if you do the testing, say you will come up with a report like this. So here you will get the basic thing is that here in this case you need at least 1 GB of random data. So you cannot this result will not be conclusive if you feed to the software a very less amount of data, so that will not be very random. So you need to have at least 1 GB of data, and it will do some test, and then you will get some scores. So here you can see that the minimum pass rate for random excursion variant test is 613 for the sample size equal to 627 binary. So for some test there is a pass marks is given here, and some test the pass marks is around 980. So depending on which test you are performing, so it will come as a either pass or fail. There is no other options. So it will either pass or it will fail. So for some tests the pass marks is around in the 600 range. For some it is around 980 range. So you need to pass all the test. If some of the test is failing, then your randomness source is not proper. So if you feed the data, all the tests are passed, then your data is secure. So this is the actually this there are multiple tests. This is just a snippet from that actual test report of a random data, and the minimum requirement is 1 GB data. So the 1 GB means 10 to the power 9 bits. Then in industry, we have two products from IDQ and Q Labs. So this IDQ RNG data we are using in our system. So you can see that the random RNG data output is around 4.9 Mbps. It is very small size chip. You can see from the chip size, and it is the NIST certified. And this Quintessence Labs is an Australian company. They have a very high bitrate QRNG source. It is around 1 Gbps, but this is a more bulky system. And this is basically configured as a PCI card that can be plugged in your systems. So these are the two commercial QRNG products. Now in India, ISC has also recently developed a QRNG, and some other IITs are also working in QRNGs. But these two are commercially available, and IIT Madras recently signed a 1 crore deal to license India's first silicon photonics based QRNG. That this is based on a news that came in the online. So they are also making some. They have also made actually the QRNG. Now, finally, I'll conclude this with the QKD networks. So, what is a QKD network? Because earlier we are talking of point-to-point QKD networks, but this point-to-point QKD network may not be suitable for all applications. And while you are connecting multiple nodes, then the network should be secure, it should be scalable, it should be stable over time, it should interoperable with different vendors, and it should be manageable. So that is the basic properties of any networks, be it QKD or some other networks. So depending on this, the ITU has come up with the standards that I showed you yesterday, ITUT Y.3800 to 3822. So this diagram I have taken from the ITUT document. So it is a very lucid standard. You can all go through the standard. So in this you can see that we have the quantum layer, that is in the physical layer we have the QKD modules, Alice and Bob. They are connected over classical channel and quantum channel. They are together called the QKD links. Now they are generating the keys and they are supplying it to the key management layer. Now this key management layer and this QKD control layer and this QKD and management layer, then all these layers are sitting inside your QKD box, but they are distinct layer because each layer has some definite functions. So what are the functions that I have given in the subsequent slides? But here one thing we need to understand is that this is your actually application link. So this is actually your encrypted traffic in this application link. This QKD node is generating the keys and it is supplying to the application layer. Okay. So here you see that there is a red mark is there. It is called the security demarcation. So it means while you are generating where you are working with QKD, you are generating keys, you are only responsible for security of the keys till you are below this line. Once the keys leaves your system and it is given to an application entities, routers or encryptors, it is not your responsibility to make to ensure the security of the keys. So that's why it is called a security demarcation. So what does it mean? Suppose you are generating our keys, then you supplied the keys to a router, and the router is now vulnerable because someone has the router password is very weak, or someone has actually captured the router. So it is not the fault of your QKD system. So this is, but while the key is inside your system, you need to ensure that this setup is proper. It is a trusted node. There is no such vulnerabilities. So that's how these layers are operating, and each layer has some dedicated functions. So here you can see that the quantum layer is responsible for generating the keys and reporting the link performance. Management layer, key management layer is stores, formats, distributes the keys. So because each key will have some lifetime, because once we supply the key to an application entity, then we delete the keys, because one key we cannot give to multiple entities. So that's why the key management functionality comes into picture. Then there is a QKD control layer, then service layer, user network management layer, and QKD and management layer that performs the FCAS. FCAS means fault configuration, accounting, performance, and security. So this type of like when you are deploy a network, you need to manage every parameter, like whether the network is operating fine, what are the quality of service parameters. So all these things are taken care by different layers. So you can go through the standard and it will give a fair overview of how to deploy a network and which layer will function at which do the which functions. So they have classified that QKD network in three types. So these types is very simple. So here is that in QKD there is a QKD layer and there is a user network. So in type 1 you can see that the user network is directly connected, but due to distance limitation the QKD have two relays. Here you can see that due to increased distance, the user network and the QKD network have same number of relays. So here it is the data relay and here it is the key relay. So it is having the same number of relays and here it is having the asymmetric number of relays. So here it is two relays and here it is having one relay. So this is a very simple classification, type 1, type 2 and type 3 types of QKD networks. They have given in the standard again in the ITUT 3800. Now I have a small before going to that, if you have any doubt, then I can clarify that. Is there any questions on the chat box? So I have actually covered the topics that are there for today. So if you have any doubt, please let me know. Otherwise, I have a small quiz. If you are interested, I can share the Google Form link. There is, I think, another 15 MCQs. Are you interested to take part in that to check your understanding? Either marks will be private to you for your information. Any
Sir,
query?
sir,
Yeah.
you can share that link. Actually, we are also conducting one quiz. So,
Okay.
हाँ तो साथ में हम दे देंगे. There is no
Okay, so
issue.
I'll share that link. Okay, any doubt, then I can discuss, then I'll conclude.
Sure, sir. Audience, if you have any doubt, you can type in the chat box or directly you can ask. Okay. I think there is no question, sir.
Okay, so I'll give you the link so you can share it to the students, and then I will share you the marks later on.
Sure, sir.
Okay.
Uh, Thank you, sir, for this interesting and knowledge enriching session on quantum communication, especially for the QRNG. And once again, thank you, sir, for your kind support and participation in Atal FTP on emerging frontiers in quantum technology and communication. Thank you so much, sir.
Okay, sir. So I'm sending the link in your WhatsApp.
Yes, sir. Yes, sir.
Okay, I'm
WhatsApp.
sending it. Okay.
Dr. Himanshu, please stop the recording.
Okay, so I'm giving my email ID. So if in case if you have any doubts in future, you can come reach to me.